Alright, today we will cover electrolysis, where we will be learning how to predict the identities of substances liberated during electrolysis from the state of electrolyte, be it molten or aqueous state, using their relative position in the redox series, which is their electropotential and concentration. So first we will cover what is the definition of electrolysis. All right, so electrolysis is defined as the decomposition of the electrolytes to its constituent element. So whatever you form, you need to make sure that the element is being formed under its standard states. So for example, if you are forming chlorine, make sure the chlorine appears as chlorine gas, all right, Cl2G, okay, not just Cl element, okay? Now, so we will take into consideration two factors. Please look at the top right corner. There are two factors that we need to consider when we want to determine which ions that will be discharged at the respective electrode. Number one, we need to look at the standard reduction potential or the standard electrode potential. Second, we also need to consider for the concentration of the ions, and this only applies to anion, not to cation. Now, so without further ado, we're going to go into the first one called the molten NaCl. There are three types of electrolyte. The molten under the liquid state symbol. You have the aqueous here, AQ, and the third example here is the saturated or the concentrated version. Now, this will be the template, all right, or the system, or a simple template or simple drawing on how the electrolytic tank will look like. Now, it will only have one tank or one beaker instead of two, compared to your electrochemical cells, also called voltaic galvanic cell. They have two separate beakers or two separate tanks, which is connected via a salt bridge, and you have a voltmeter. All right, for electrolytic, we need to use a power source, which is a battery, and we will put our electrolyte in the tank, and then it will start to decompose to its constituent element using electrical energy powered by the power source. Okay, now there are three examples, and the first one I want to discuss is using the molten NaCl, which is the easiest among all. Now, first we need the electropotential, and I have extracted the E value, all right, and I arranged from most positive to this positive, as you can see down here in the table here. Okay, now more positive E value means the reactant will undergo reduction with a higher probability. Okay, now molten, you have Na plus and Cl. So first, I would like to label in my electrolyte here, Na plus, Cl minus. Okay, now then your battery, the long one is the positive and the short one is the negative. Now, knowing the electrode, all right, which electrode is positive, which electrode is negative, according to the symbol of the battery power source. Okay, so now we will have to assign which ions in your molten NaCl will move to which electrode. So please remember that cation move to the cathode, anion move to the anode. So I'm going to write this. Cation move to the cathode, and ion move to the anode. Okay, now what is made of your electrode here? Please label platinum. Why platinum? Is because we want to use an inert electrode. Option 2 will be graphite. Okay, so you can always put graphite or platinum. So next, we will assign where does the Na plus and the Cl minus move. Now, according to opposite charge attract, we know that the Cl minus, which is chloride ion, will be attracted to the positive electrode over here, as you can see. So chloride will move to the right-hand side, and sodium, being positively charged, will move to the negative side of the electron because opposites attract. Okay, So now when I know which ion moved to which electron, then I ask myself, chloride is an anion. And then anion will move to the anode. So now you know that this lake is called anode. All right, now on the left-hand side, I ask myself, Na plus is a cation. And then follow the principle, cation will move to the cathode. So therefore, on the left, this is our cathode. Okay, so the first principle you learn here, number one, is which ion move to which electron. Okay, and it is due to opposite attract. Okay, now number two, what type of reaction is at the anode and what type of reaction is at the cathode? So principle number two is this. Anode is always oxidation, okay? And cathode is always reduction. This is a principle number two. So if you know anode is on the right-hand side, that means oxidation is on the right. Cathode is on the left-hand side. So far, you need to memorize these two principles, okay? Yeah. Now, then can we construct an equation here? Okay. Now, we can construct an equation. Okay. So I'm going to change to another color. Let's solve the right-hand side first. Since we know that chloride is an anion will move to the anode, and on the anode will always be oxidation. So oxidation means donating electron, hence your half equation would be this. Like this. So you can see 2 electrons were donated. All right, now on the left, Na plus is a cation. Cation move to the cathode. Cathode is always reduction. What is reduction? Receiving electron. So you construct an equation to show Na plus receiving electrons to form Na. Now then you check with yourself the definition. Electrolysis is the decomposition of the electrolyte to its constituent element. Is currently chlorine existing as chlorine Cl2 gas? Yes, my equation do show Cl2. Okay, if you want, I can put the gaseous state here for you. And you check on the left-hand side, sodium. Sodium currently now exists as Na solid. Yes, you form deposition. All right, so if you want, you can start drawing, perhaps some deposition of the sodium down here, or maybe the electrode becomes so-called larger, okay, here, okay, because the coating of the sodium metal on the platinum electrode. Okay, now, so this is a very basic first step on the electrolysis in terms of identifying which ion will be discharged, because molten, you do not have any competition of the cations and a competition of the anion. So it's a quite straightforward case. Okay, yeah. Now, then you can copy the two equations over here, like I highlight here and here. Okay, you may want to write your two equations down here. What happens at the cathode and what happens at the anode? So we're going to quickly write what happens at the cathode. So cathode here will be this. And the anode will be this equation. Now to construct the redox equation, we have to multiply the first equation by 2. And then you can cut, all right? The 2e. Oops, sorry. Oops. Just give me a moment. Here. So yeah, you have to cut this. These two and these two. All right, the first equation multiplied by 2. Hence, the balance equation for the redox that occurred is this. Okay, that will be your molten case. Okay, so now let's move to another example, which is more frequent. Okay, aqueous state. Okay, aqueous. Now, aqueous means your sodium chloride was dissolved in water. Okay, that means you have H2O and you have H plus and OH minus inside. So the Na plus and the H plus will start competing, and the chloride minus and hydroxide, so-called negative charge, will also start competing for the same electron. Okay, now, so let's move to the diagram. Okay, now first principle. Okay, first principle. We learned that cation moves to the cathode, anion moves to the anode. Okay, so first label your ions. Now the ions label over here is Na plus, Cl minus, H plus, OH minus. Okay, now your battery symbol, the long one is positive, the short one is negative. We know that negative charge ions will move to the right electrode, all right, and the positive charge ions will move to the left electrode. So now we have to make up our mind, all right, between chloride and hydroxide, who will be discharged at the positive electrode. Okay, now first, chloride hydroxides are anion. Anion, they move to the anode. Okay, and hence on the left hand side, the cations will move to the cathode. Okay, now between chloride and hydroxide, who will be discharged? Okay, so now you have the third principle. When it comes to anion, okay, we pick the more negative E value. So please put your attention down here. I circle up chloride, I circle up hydroxide. Now, please be reminded that arrange your E value from the most positive to the least positive. When you arrange, okay, it will be more clear to make your decision. We will pick the more negative anion to be discharged. So between a positive 1.36 and a positive 0.40, we will pick a more negative version to be discharged. So hence, the hydroxide will be discharged at the anode. Okay, now principle number 2, anode is always oxidation. So hence, you can reverse the equation given from the table to show an oxidation reaction occurred by donating 4 electrons. And yes, you do see oxygen gas liberated. Is oxygen in its standard state O2 in gaseous state? Yeah, so you fulfill the definition. Let's move to the left-hand side cathode. Okay, now you have 2 cations, sodium ions, H plus ions. Now, the principle here is for cation, we will pick the more positive E value. Okay, so we want to look at H plus and Na plus. We will pick the more positive, which is 0.00, compared to a negative 2.71. Okay, so the more positive ions, which is H plus, will be discharged at the cathode. All right, so principle number 2, cathode undergo reduction. So you can just copy from the table if they provide to you the equation on the left, reduction here. Reduction means receiving electrons. And yes, you will liberate hydrogen gas. So sometimes in drawing, you may want to draw a inverted test tube, something like that. Then you start collecting hydrogen gas. You can test with a burning splinter, a pop sound will be produced. And over here, you start collecting oxygen gas. You need to put a glowing splinter, then it will relight. Okay, so hence we will copy the equation, all right, for the anode part. I'll just quickly plug it in here. Okay, and your cathode here, which is the reduction. Okay, so the first equation is to multiply everything by 2. Why? Because we see 4 electrons here, and up there only got 2. So I need to balance the electrons for the 2 half equation. So this one will be 4, this will be 4, this would be 2. So therefore, receiving 4 and donating 4 can cut. Okay, so hence the redox equation will be 4H plus 4 hydroxide to give 2 hydrogen gas plus 2 H2O plus an oxygen gas. So we do see the production of the constituent element from the electrolysis. Okay, so we have discussed the second example using aqueous state. all right? Now, so based on this second example here, where we look at the sodium chloride aqueous state, all right, we actually use factor number 1, which is the relative electric potential, to decide which ion will be discharged. So everybody, okay, the first factor we have covered, which is number 1. If this is an anion, okay, we choose or we pick the more negative E value. Okay, now for cation, we choose the more positive E value to be discharged. So this is using the E value to know which ion will be discharged when you have a competition, which most of the time it will be aqueous ions. Okay, now let's go through the last example. Now the last example, we will involve factor number 2, which is the concentration. Now concentration only applies for anion. So let's look over here. I highlight in pink color. Concentration only affects anion. All right. Okay. Now, so the third example here, we play with saturated or concentrated NaCl with aqueous. So first, aqueous means you have competition of the cation and competition of the anion. Second, you have a concentration to also factor in our decision making. So maybe I should start erasing a little bit so that I can have space to write. Okay, so perhaps just erase a bit. Okay, so let's look at the last example, which is the concentrated or saturated NaCl case here. Okay, now same thing, we will start labeling our power source. Long arrow means positive, short arrow means negative. Now same thing, I have Na plus, Cl minus, I have H plus and OH minus because it's aqueous. All right, as you can see here, look at my cursor, aqueous. So you have a competition. Okay, now and then you want to play with concentrated. Okay, concentrated means, okay, you have a higher concentration of the Na plus and the Cl minus. So I'm going to use my red color pen to put an arrow upwards to indicate Na plus and Cl minus concentration is higher than H plus and OH minus. Okay, now first, we will settle the cation first because concentration only affects the anion. We only play concentration for anion. We don't play concentration for cation. So we would like to solve the cation first, which does not involve concentration at all. So regardless of the concentration, we have learned that for cation, we'll pick the more positive version. Okay, so hence, put your attention at the table again. So you have H plus and Na plus. Okay, for cation, we pick the more positive E value. So H plus is the more positive E value, so it will be discharged. Now, knowing H plus, principle number 1, cation move to the cathode. So on the left, I label here cathode. Cathode is always reduction. That will be principle number 2. Okay, so hence we know that the equation here will be 2H plus 2E to give hydrogen, which is the constituent element. Hydrogen now is H2 gas. Okay, now for anion, we have to factor in concentration now. Now let's not talk about concentration first. We go by status quo. According to the factor, according to the E value factor, okay, for anion, we will pick the more negative. Okay, so I circle chloride, I circle hydroxide. We will pick the more negative E value to be discharged. That is under status quo or normal standard condition. Okay, but because now your chloride has a higher concentration, okay, now please look at this equation. I will put an arrow up here indicating chloride high concentration. Now you have to bring back the Chatelier principle. So when you have a higher concentration for the chloride ions on the right-hand side, the Chatelier principle will try to counteract it by reducing the concentration of the chloride. So the equation will shift to the left-hand side just to counteract the high concentration of the chloride. So when you shift left, what will happen to your positive 1.36? What is E value? or what is standard reduction potential? The ease of undergoing reduction. So if you favor reduction, that means your number will be more positive. But currently now, you are shifting to the left. To the left means oxidation. That means you're going against reduction. So if you're going against reduction, you do not really favor reduction. That means your positive 1.36 should not be so positive. So what happens actually is the positive 1.36 will actually be more negative, okay, then until the point that it surpasses the positive 0.40. All right, so now the more negative version is actually here, which we do not know the value, but of course this value can be calculated using the Nernst equation, okay, yeah, which you will learn another lesson. Okay, so the new value for the chlorine gas and chloride ion is no longer positive 1.36. It should be less positive or more negative. Why? Is because according to the Shatterer principle, they are undergoing oxidation, all right, just to counteract the high concentration. So now the new, more negative value is your chloride. So if you really want, I can write the true level of the chlorine and the chloride inside here. So perhaps this is the true value here. There's somewhere in between. Now, therefore, your new competition is between here and here. Hydroxide now is positive 0.40. Your new chloride level is more negative than positive 0.40. So according to the first factor, relative potential, anion always pick the more negative version. That's why chloride will be discharged in this case. So chloride, okay, is in anion. Anion will move to the anode. Anode is always oxidation, correct? So therefore, you will form your chlorine gas like this. Okay, remember, concentration only affects anion in your syllabus. All right, we only play concentration in anion. So if you were to plug the two equations down here, so cation is this, and anion is 2 chloride, donating 2 electrons to give chlorine gas. These two and these 2 electrons can cut, hence 2H plus 2 Cl minus to give hydrogen gas and Cl2 gas. All right, so if you want, you can draw, all right, over here. Okay, you will start collecting a yellow-green gas, right? Chlorine is a yellow-green gas. Okay, and on the left, you will collect a hydrogen gas here, something like that. Okay, so therefore, we have already used the 2 factors to know which ion will be discharged, okay, using 3 examples. The first one, molten NaCl, do not have any competition. So you are the only cation and you are the only anion. You move to your respective electron for discharge. The second example I gave was Aqueous, where you have a competition between the cations and the anions. All right, and then we learned that for anion, we pick the more negative E value. For cation, we pick the more positive E value to be discharged. Okay, now lastly, when you want to play concentration, all right, concentration only affects the anion, okay, and you need to use the Shatterer principle, all right, to counteract the high concentration of the anion. Okay, please be reminded that concentration, also called high concentration of cation, is not applicable. We don't play with high Na plus, or any form of ions in making our decision to which ion to discharge. Okay, hope that helps you to clarify. Now, before I end this video, all right, you may want to go through a couple of few statements that I've written down here and the principles that I've brought, or so-called inform, all right, about this video. All right, there's another thing I want to bring up here. It's the box at the bottom right corner. You have a series of anions, all right, which is given in your textbook, Cambridge Press. Okay, so what we can see here that if you look at your data booklet and using the syllabus, all right, but of course with the 2022 to 2024 data booklet will not be provided. They will print the information on your question paper itself, okay? But this is just for education purpose. You will see that there's a sequence according to E value where sulfate ion, all right, is the most positive one, followed by nitrate, chloride, okay? But hydroxide actually, according to E value, should be all the way at the bottom here of 0.40. Okay, now if I'm not mistaken, I will just quickly have a look what is iodide. So to complete the whole story here, for iodide, iodine is, just give me a moment. Just extract the data for you. Okay, bromine, bromide 1.07, 0.54. So let me just write on the screen. This would be 0.54. And bromine, bromide is 1.07, positive, huh? Now, so you can see that the increasing ease of discharge is actually moving from a more positive number, all right, to a less positive number. That's why you see 1.07 for bromide, 1.54 for iodide. Okay, now hydroxide being 0.40 should be at the last. But what you realize is hydroxide, according to your textbook, they actually inserted hydroxide in the middle here, which is unusual. Why? Because if you look at the chlorine, which happens to be 1.36, right? And you start inserting a 0.40 E value here, which is not correct according to the number, okay? So there is a so-called preference when it comes to which ion will be discharged at the inert electrode, and I'll suggest that you memorize this sequence, even though the data booklet in your table can help you to make the decision where we pick the more negative anion to be discharged, but I highly suggest that you memorize your chloride, hydroxide, bromide, and iodide, at least this four. Right, just to let you know, sulfate and nitrate will not discharge at your level. Okay, yeah, so you can safely cross out sulfate and nitrate. You just need to memorize this four sequence: chloride, hydroxide, bromide, iodide. Okay, so it means that if you have a competition between chloride, hydroxide, bromide, and iodide for the same electrode, which is the anode, because anion moves to the anode, iodide will be discharged first, and anion will undergo oxidation. So you will get iodine, I2, be it gas, be it solid. Okay, they exist in two forms. Okay, so you need to know this particular sequence, which is this four. Because if you want to solve your previous past year question, you have to use this sequence to solve. Otherwise, you cannot make sense of the marking scheme. Okay, but yes, you still need to hold to your principle where anion, the more negative E value will be discharged, but you just need to take note if there's a higher concentration, therefore the higher concentration anion would normally be discharged due to the Le Chatelier principle to counteract the high concentration. And before I end, please remember that four ions there. Okay, chloride, hydroxide, bromide, iodide, increasing ease of discharge at the anode. All right, and I'll see you in the next video.